Hello, hackers. Wait, shit. As usual, we're not following. We're not on the what's it called? Yeah, the Twitch. Okay. Awesome. Now we're on the Twitch. Are we audible? And maybe. Perfect. Okay, we got the chat. We need to get followed. The camera needs to like and subscribe here. What is this? I solemnly swear I want to know good. There we go. No. The L is. I think it's L. You think so? It does. All right. Got it. Awesome. Okay, we're live to nice 7 people in person and 17 on Twitch. Everyone else will fail. Okay, cool. Welcome to week 2 of binary exploitation. How did the checkpoint go? Let's see how the checkpoint went. Let's refresh this. Okay, 1, 2, 3, 4, 5, 6. Oh, it's a little tricky. Okay, because we had people going through the easy ones. It's hard to actually tell how to went. What I'd guess probably about 3/4 of the class checkpointed. Cool. Awesome. So you've now kind of dived into understanding how the kind of integrity of memory in software breaks down when things like buffers are overwritten and so on. What you have to look forward to is putting all of this into practice. And so far, 23 people, let's say, have solved everything. Not quite, actually. 12 people have solved everything. For the rest of the class, you're staring down a deadline during Thanksgiving weekend, especially the 8th person that just walked in. That might be a little daunting. Similar to, what was the other one? Yeah, fall break. Similar to fall break, we're going to try to reduce the pressure on you by giving a 3-day extension to reverse engineering, to binary exploitation, with the understanding that we'll still launch the next module on Monday, but binary exploitation will be due on Wednesday evening. All right, so it's up to you to manage that. Our strong advice has always been finish the module as soon as possible, and about 20 or 30 people take this advice. But do with this extension what you will. So binary exploitation to take some pressure off of Thanksgiving and let you have some Thanksgiving time with family. Will be due on Wednesday, but the next module will still launch on Monday. So if you don't have any Thanksgiving activities planned or whatnot, or if you have a free day or two around then that you're not spending doing Thanksgiving or family stuff, please don't neglect binary exploitation. Should do your binary exploitation exercises every day. What else? Oh, we also applied extra credit. Almost everything should be in. There's still a couple of the very last surveys missing. It's a semi-manual process. And everything else should be in, right? Including extensions. Yeah, everything, all extensions should be applied. All CTF, archive, extra credit, all helpfulness, all memes, everything should be good to go. If you check your grades page, you see your new upgraded and updated grade. I think the median now in the class, of course, this class is hyper hard, et cetera, et cetera. I think our median is 90%, 89 or 90. We'll have better numbers for you next class, but overall, between you know, curving when it's you know, when we made challenges or modules overly difficult, and extra credit to help reward the memeing, the peer-to-peer help, and the um, applying your skills by tackling these kind of free-form CTF exercises. We've got a good amount of people doing really well. So take a look at your grade, realize how hard you worked for such an awesome grade, and then, full of this energy, go and do your teacher course evaluation, please. So the teaching course evaluations launched on Friday. You probably got an email about it. They're open for another like 10 days until December 5th. So go do them. That's important for us. It's good feedback for us. And also good feedback for the department. You know, it's one thing for us to go in and say, hey, look, you know, we need to teach more Python earlier on in the computer science curriculum, for example. If I just go on and say this and say my students of blah, 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 carries a little more weight if that shows up in evals like, hey, this class was super awesome. We loved it. It's great. But I wish I had more Python early on. See, that's actionable feedback, for example. You know, delete this class from ASU. It's also actionable feedback. But, you know, the important thing is everyone gets a chance to voice their feedback. All right. And then hopefully we can improve things next semester and the semester after so that we can show an upwards trajectory and argue for our continued existence. Okay. Awesome. With that, anything else administrative?
I don't think so.
Anyone got questions? Binary exploitation. The next module, there is one more module. For some reason, this is very unclear. Let me just show you the syllabus. I just want to make sure that we have the extra module on there, the last module. It's loading.
Bench had to be improved.
Yeah, why is this take so long to load? Oh, computing all the grades. Okay. Yes, so where the hell is the schedule? There it is. All right. We're currently in what is called binary security. We need to update this name because we have put binary security. I'll update it to binary security. Rename the actual thing. And then the next module is going to be end-to-end crazy exploitation using multiple things that you've learned throughout this course. So you will corrupt some cryptographic, you'll intercept communications that are using cryptographic channels to like corrupt the crypto to overflow a buffer to execute shellcode. Like it'll be crazy stuff. And you will feel like absolute rock stars. Anyways, all right. It's gonna be awesome. Okay. So, but in the meantime, let's try to get you through kind of surviving binary exploitation. So far, with binary exploitation, we've covered kind of the basics of opening up a binary and looking at potential areas where an overflow might occur, calculating out offsets using both static and dynamic techniques, and overflowing the buffer. And you covered hijacking the return address. Hijacking the return address. What we haven't gone into too far is the later levels that people are now starting to get to, which is shellcoding, and then actually putting it all together, having shellcode that's injected into a binary, into a process memory space, and then jumps to. So We're going to talk about this today, talk about approaches to debugging shellcode, and go from there. To avoid, that's interesting, to avoid, I need to start a challenge. To avoid giving away too much, we're going to make shellcode that, I don't know, prints high instead of making shellcode that gets us the flag. But we will go through kind of an end-to-end how to write shellcode, which should look very, very familiar, and how to inject it into software. All right. Sounds good? Everyone amped? Everyone's amped. Silently amped. Okay. Shellcode level 1. We have a challenge that reads your shellcode and executes it. I'm just going to put a bunch of A's because that's what you're probably used to now. And it says, oh shit, our shellcode didn't disassemble. And when it tries to execute it, gets a segmentation fault. You can't just type shellcode in. I mean, you can actually, but it's very hard to type useful shellcode in. Although it would be awesome to memorize an alphanumeric shellcode and just be able to type it out. That's goals for next semester. But what I can tell you is if you just type poo-poo over and over, these are actual instructions that disassemble into something, right? So this pushes a bunch of registers to the stack and then crashes. So you can type in bytes, and even printable bytes are like x86 instructions. But the point with shellcode is to create an actual program that is injected into the process memory space and runs, right? Now, when you create an actual program, let's create a hello world in assembly. Okay. What do we do? That Intel syntax, no prefix. Here's our start. Now we're going to move RAX1. That's the write system call. We're going to let's move into the into RSB. How do we do this? Is there a? I'm drawing a blank. We can't do this, right? Of course we can't do that. We're just gonna put a bunch of A's. So in little endian, this should be 414100. No, it's the other way. So this should be AAA with a null byte afterwards that we're writing to the stack pointer. We're going to put this the write syscall. Hopefully this is all review from Computing 101. The write syscall to RDI. First argument is the file descriptor to write to. Second argument is the buffer. And that's our stack that we just wrote AAA to. So this should print AAA. And in fact, let's just print AA with a new line just to make things even nicer for us. And you know what? Instead of AA, let's print high. So A, B, C, D, E, F, G. I missed something. I just failed at a B, C, D, E, F, G, I. Okay, perfect. No, 48 and 49. Should be high. Wow, that was awesome. So that's in my defense, I was in Spain 2 days ago, so I'm a little jet lagged. Yesterday, my night just was me laying in bed staring at the ceiling. All right, and then the number of bytes to write RDX, 3 bytes, HI new line, and then we do a syscall, and boom, everything works. All right, you've done this in Computing 101. Who here has done this in Computing 101? All right, everyone is amped. We've done this in Computing 101. We assemble, we link, And we run. And it says hi and then crashes out. Amazing. Let's actually stop the crashing. Just we'll exit out with whatever other value. All right, assemble, link, boom. All right, so this is all review. Now, when we run this program, and I'll do this in GDB, and I do start I, and I print these instructions. Here is our shellcode, right? Here's our program that we wrote in assembly. It's loaded in the process's memory space at this 401,000, and then it just runs, right? How does it end up in 401,000? It ends up here because when we assemble it and link it, we link it into this hello file that is an ELF executable. And the ELF executable, and here I wish that we had did we have the ELF file lecture assigned for Computing 101, right? You all watch the ELF file lecture? You know what an ELF file is and everything? An ELF file is much more than just these instructions. These instructions, we have, I don't know, some small amount of bytes, maybe 24, a couple more than that, right? An ELF file read ELF. Yeah, an ELF file has a bunch of metadata. And one of these pieces of metadata, so it says, you know, for example, this ELF file is for a Unix operating system that follows the system 5 ABI, which happens to describe Linux as well. It is a 64-bit x86 binary. The entry point where execution should start is at 401,000. And it has in the file a bunch of other information that describes here what to load and where into memory from the file. And so it says, okay, at memory address 40000, I want you to load 150 bytes from the very beginning of the file. And this is all hex 150, hex 400, into 150 bytes at this memory address. And if you recall our entry point into this program at 401,000, and we saw this when we were running GDB, where our execution started, we can say we have a directive here in the ELF file to load from file offset hex 1000 to virtual address hex 401,000, which is where our execution starts, our entry point, to load hex 2A bytes into this address, hex 2A bytes, and make it executable, that memory. That is where our actual code is. So we wrote our code in assembly. It assembled to hex 2A bytes. That's 42 bytes that it then will load when this ELF file runs into this 401,000 address, and all is good. And in fact, if we strace the execution of hello, no, I guess it won't. If it was loaded additional libraries, we'd see it. But the kernel loads that guy, right? Yeah. Anyways, if you write a program that loads other ELF files, we would see it actually reading out parts of the ELF file, loading into memory. But we're not we didn't do that, so we're not going to do that right now. But anyways, this ELF file has these program headers. And if you actually just like hex dump this ELF file, we see a lot of stuff, including these program headers. Somewhere in here is going to be hex encoded the addresses. Here it is, 401000 in little endian. That is literally the load directive to load data into memory. Here's the 2A, that's the size in the file. Here's the size in virtual memory, the same, 2A. Here is the size, the offset in in virtual memory, 401000. Somewhere over here is probably going to be the entry point if we scroll around. But anyways, it's not a huge, but you know, all of this data is there. And then if you recall, at hex 1000 in this file, right here, nope, hex 1000 in this file, right here should be the start, the entry point, the start of the data that gets loaded into memory at the entry point of the program. And here it starts out 48. That's a good sign. That is a instruction prefix for the 64-bit operations. C7, C0, 10. Let's remember that. Scroll up to where we disassembled. We don't have the bytes. Let's disassemble the binary. Hello. Disassemble the start. Here it is. 48, C7, C0, 01. Sound familiar? This is literally where the bytes are stored in memory, right here. Super cool, huh? So now we have written a program, but a program is not shellcode. If we inject, if we look at what the shellcode is doing, this challenge, and it kind of simulates what you will be doing later. This program will read in your shellcode. Where is it? Allocated reading. It reads in shellcode. It'll disassemble it so you can be sure that you sent what you want, and then it'll just execute it straight up. It basically treats the pointer to the shellcode data as a function pointer and jumps there. Cool. If I send along my entire ELF, like that, then what happens is there's a lot of data here, including, if I just hit less here, including some crazy stuff, starting with 7F45, that I can see is actually at the beginning of my ELF here. Every ELF file starts out with 7F and then an ASCII ELF. And that's what it's trying to execute, metadata in my ELF file, right? But it's trying to treat my shellcode as a function. And that is what your shellcode is, really. In some sense, it's just a function that you're trying to inject into the process's memory space. But instead of a function, we brought an ELF to a function fight, right? And it's trying to execute the ELF, and it is failing because whatever this is will probably immediately crash, or if not, this stuff, these aren't intentional, careful instructions. This is garbage that's being executed. So what we need to do is extract just the code and have that executed in the process memory space. In order for that to happen, we need to grab those bytes that are right at the beginning here, or not at the beginning, that would be loaded at that loader, like these bytes, these 42 bytes, and send them in. Okay, how do we do that? There's a number of ways to do it. One way is we can actually do something crazy. Don't do it this way. This is the everyone's going to do it this way now, but it's fine. Go back to our read elf. It's our nice interpretation of the elf headers. We see that at the file at OX1000, there's 42 bytes of shellcode. So we can use the DD. What does DD stand for? I used to know this. Data dump. Maybe duplicate, divert, and copy a file. Anyways, all right. We can go dump data from the hello file. This is the output of our assembly into, or our binary, into our kind of raw, let's say, shellcode, and an offset of the file of hex 1000. Can I do hex here? This is going to be a disaster. All right, it's fine. Hex 1000, and we say we need a block size of 1 byte. This offset is specified in blocks, and then we say dump 42 blocks, and we hit enter, and it says hex is no good. All right, it's fine. Here's what we can do. That's bash will interpret the hex for us. Unrecognized operand offset 4096. Is it not offset? Am I crazy? I've been using DD half my life. Skip. See, we skip the first hex 1000 bytes. And boom, we copy out 42 bytes into hello.shellcode. We're going to dump this to make sure it works. Here it is, 48C7C001. Freaking awesome. All right. Now we do that again with our shellcode. And it disassembles properly and it executes properly. And we're heroes. Cool? So what did I do? I used DD, which you should not do it this way, but I use DD to extract the bytes I need right out of the file by interpreting the headers, figuring out where they are, and typically in a small elf like this, without addition options, they'll be at hex 1000, and pull them out. Now, that's because I'm a crazy person. You shouldn't do that. There's really good tools, such as obj-copy, and obj-copy has an insane usage. But there's a reasonable usage, and then there's what I usually do, which is an insane unreasonable usage. But here we have an awesome reasonable usage. So we just say obj-copy, and we say copy into this hello. That shell, we'll do shellcode 2, just so we can compare it to 2. And we say only copy what is called the .text section of the binary. That is, the elf has some other metadata that actually says all of the code. Text doesn't stand for like, reading text. It stands for something. What does it stand for? I knew this recently. See, I'm fading. Maybe that's
what it is.
Maybe I have some just a couple of extra semesters in me, and then it's over. All right. Anyways, the text section is where your code gets put in. You can see this is the section that's executable in the binary, and that section is at 401.000. As the lecturer explains, the real workhorse of the ELF are these segments that say, the program headers that say, we load into this part of memory from this part of the file, the end. the sections, all of this stuff that gives you more semantic information that, okay, here, this is the text section that starts at this 401.000 that's loaded by this load directive. That's all. This is all for human use. None of this matters. The point is that we take the text section and no. -O is the output format. My bad. It says we're gonna dump this in raw binary, and we're gonna say what we're gonna dump it from, and you can use either hello.o or either the raw assembled version or the linked version. And I think it shouldn't matter for these challenges. And then we dump it out into hello shellcode 2, and we can dump out hex dump hello shellcode 2, and we have the same shellcode. Here's 2, here's 1. 2, 1. Same way of doing things. What OdgeCopy does is it reads my elf's headers and carries out what I did. It looks at, well, where's the text start, where's the execute, blah, 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 and it dumps that out. All right, the two are equivalent, and in the same vein, of course, they're equivalent, so this is a foregone conclusion, but here it is executing just fine. All right. So now we've executed our first shellcode, right? But let's say that we did all of this, and in the end, I messed up, and I, instead of moving RSP here, moved RDI for some, I just didn't notice, right? What's going to happen here? We're going to crash. So let's assemble, link, dump, and run. And we didn't actually crash. We just didn't get output. Why? Because we put some bizarre, well, why? Because we did something wrong. First thing I do, personally, when my shellcode goes wrong, is how do I do home again with Emacs bindings?
Control A.
Oh, that's what I tried. All right, it doesn't matter. All right.
Assuming home is Control A.
First thing I do is strace. So as something goes wrong, I strace this, and I see, okay, it says executing my shellcode, and here is that shellcode, and it's wrong. Something is off. I can clearly see that the write fails with a bad address. The exit succeeds, but this write fails. Now, I know what happened because I just broke the shellcode. But what if you didn't know what happened? How would you debug shellcode? When you need to debug your program, you know how to do it. You have your good friend GDB that everyone uses very enthusiastically, right? And I would GDB this program. I would run it with hello.shellcode. Oops, hello.shellcode 2 is the broken one. And then it just kind of executes the shellcode and fails. That's really annoying. And so say, okay, well, that's fine. Let's figure out where the shellcode gets launched. And now I can reach for a number of tools. I'm going to reach for IDA. Okay. Here we are. Here it is. This is where the shellcode gets launched. This is the actual indirect call of the shellcode. And if I look down, I can see that it is at main plus 29D, also known as, oh, this is a position independent binary. God damn it. All right. So we use the symbol offset main plus 29D. All right. Then we run. Now we have our breakpoint. Okay. Here it is. Call RAX, call RDX, and boom. Look familiar? This is our shellcode. All right. So I can break where the shellcode is about to be run, and then I can just start stepping through it. Right. Step. And then I can see, oh, well, that's weird. RDI is being set to 1 here. Or if it was set to some other output of something, I could figure out what's going on. And then I can adapt my shellcode as I understand what's happening, right? So I step, I say, okay, well, what is RDI? Oh, it's weird. It's 1, etc. Okay, cool. So now we've kind of gotten into debugging our shellcode. The key thing is when you are running the program, when you're looking at the program here, this RDX, this stuff doesn't exist in the binary itself. Your shellcode is something that gets injected at runtime, which you can still introspect and debug with GDB, because GDB works at runtime. You can't debug your shellcode with IDA or IDA has a debugger, but you can't debug it by reverse engineering the original binary in IDA. Something that you have to, conceptualize in tandem with the running process. Now, that was a pain in the ass. I had to reverse engineer the original program, figure out where things are getting hijacked, break their step. If my shellcode is long or involved in any way, it's going to get really old stepping through my shellcode, the first couple of instructions every time, et cetera, et cetera. And actually, I don't want to keep figuring out where to break and so on. So here's an interesting thing. When you set a breakpoint in GDB, all that GDB does is drop in a special instruction. There are different settings for this, but all that GDB does in this case is it drops in a special instruction that says, hey, there's a breakpoint here. And that instruction, when the CPU executes, it'll pause the program that just executed it, and it'll say, is there a debugger attached to this? And then it'll wake GDB up and say, hey, we just put a breakpoint in, or we just hit a breakpoint. That's how GDB works. When you put a breakpoint somewhere, it has a special instruction. And in fact, I'm going to show you this in actual practice, which is probably a terrible idea, but if you're going to do it. So instead of this, we are going to move or load RSI, RIP. This is a terrible idea.
Yeah.
We're not going to do it. All right. But it would be cool to do it. Yeah, we're not going to go off this tangent. If the binary wasn't position independent, I would show you, but it is position independent, so it's too much of a pain in the ass. No, I got it. Okay. All right. We can do this without any shenanigans, so we're going to do it anyway. All right. So we're going to break at main. Oops. We're going to break at main in the shellcode runner binary. We're going to run. This is going to blow your minds. All right. So we're in a breakpoint here. Let's drop in here, see what we're running. Okay, we're running address 6737. Might need to be root for this. All right, not address, PID, process ID 6737. So every process, and we get to use DD. This is awesome. Every process exposes its entire memory space, or Linux will expose its memory space in the proc file system. It's PID. There's a bunch of information. For example, you can see all of the files that it has open, right? So standard input is being redirected from the shellcode. Standard output goes to the terminal. Standard error goes to the terminal. You can see a lot of stuff. You can see what the executable is. That's cool. Just an enormous amount of information about processes here. A lot of shenanigans that you can get up to here. You can see what its current working directory is. All of this fun stuff. All right. A very interesting thing that you can also see is its memory. Now, I can't just cat out its memory because there is no memory at address 0. But what I can do is use DD to seek to a specific address and print the memory out. So I know that main is at this address. I'm going to print it to standard out. Skip this many bytes. But okay. And let's just print out, I don't know, 16 bytes. And we'll hex dump it. And here it is. We read straight from the process memory space. We can confirm this. Here's sub RSP hex 1000. We can print 16 bytes from our IP. 4881 EC00. 4881 EC00. Amazing, right? So we are able to actually introspect the process's memory space. Where the fuck's my breakpoint?
GDB, when it's paused, gets rid of all the breakpoints until you continue because it doesn't need to limit.
Fucking piece of shit, GDB. But that's fine. We're going to restart this without redirecting something to standard input. So then it'll wait. All right, here's our breakpoint. Now we have a new address because this is position independent. And a new PID. 524. Okay. And here we have new address. Okay. Here's our 48. Okay. So this is our normal memory. And we put breakpoint. If we put a breakpoint right here at start, right? And here it is. Okay. Now this is GDB's view of it. This is where we have a breakpoint. Wait. This is not where we have a breakpoint. We want actually to put print main. Main is at a different address. This is where we should have a breakpoint. Oh, God damn it. Why didn't it paste a copy? Oh, it did copy. 47? 47. All right. Here's where our program starts. F3OFLEFA55. Here it is. OF1EFA. What the hell? Why is it different? OF. Oh, no. Yeah, here it is. F3OF1. All right, perfect. So we have our that's where our breakpoint is. And in fact, no, it broke. Oh, our breakpoint is at main +8 because it automatically breaks past where you saved the base pointer, right? Where did we do a breakpoint? Boom. 154F, 54F. Okay, my bad. It was, no one's going to follow this anymore, but we'll do our best. We'll soldier on. All right, here's the code that we also see here. Let's just pretend all is fine. Everyone understand what's going on. If I continue in GDB, God damn it. No, I don't need a loop. I just, it still redirected the same thing. Because if you hit run, it uses the previous. All right, it's fine. We will set this assembly flavor until break at main, run. All right. Here's our breakpoint. Here's our new address of main. We have a new PID, 8205. Okay, let's take a look at here is our bytes in memory, like the actual binary that we're executing, the actual memory space of the process. And if you're not looking at this in IDA, these are the actual bytes. It's amazing. And now if I continue here, it's waiting and it's running and it's reading my shellcode. Now, when the program is running, the way that GDB, again, implements breakpoints is it plops special instructions to replace what it is, the instruction at which you have a breakpoint. So let's take a look at this memory again. It used to be 4881 EC, that first instruction. Now it's CC81 EC. CC is a single byte x86 instruction that will break in GDB at that memory location. And that's how GDB does breakpoints, right? When you say break at main, it'll look it up and say, when the program is running, I'm gonna rewrite that byte with hex CC. And then when that's executed, when the CPU executes that, it'll pop back into GDB, into the debugger, and say, hey, the program hit a breakpoint. On x86, by default, that's how breakpoints are implemented. There's other ways to do it, but this is the simplest. All right, and this is what's used by default. So now we've observed this in practice. What does this have to do with shellcode? Well, we can put gratuitous breakpoints in our shellcode to help us debug stuff. This is incredible. Check this out. We exit out of this whole thing. That's all behind us now. What the hell? All right. We look at hello.s and say, okay, somewhere here, things are getting messed up. And I suspect that it's happening at this syscall already. And I'm going to stop right here and look around. The instruction that hexcc, that encodes to hexcc, is called int3, interrupt 3. It's a historic, part of the x86 CPU architecture specification. It is an instruction that interrupts your program. There are many different interrupts. This one causes a breakpoint to occur. And again, just as before, I can assemble it. I can link it. And if I run this now, it tells me that it hit a breakpoint. If I copy it out, and then if I do my binary, the shellcode runner, and I insert my shellcode, okay, I hit my breakpoint. Here's my int3 instruction. And if I GDB this, then without having to do anything else, boom, we are in my shellcode in a breakpoint that I inserted at about to execute a syscall. Pretty cool, huh? If I look at the instruction right before that, here's my breakpoint. Here I can now say, so I'm like right here, I can now say, okay, let's look around. What is RDI or our SI? whoops, RSI is the wrong thing. It should be the address of our buffer, et cetera, et cetera. We can debug our shellcode, fix it, or poke around, modify some things at runtime to see how they'd work, and then hit continue. So for example, if I have a hypothesis, let's run this again. Okay, we're in a breakpoint. I can look around and say, oh, our DI doesn't look, or RSI doesn't look so good. Maybe I wanted it to be the stack address. Like, let's say, what if I say that RSI should be the stack pointer? Okay, boom. That's cool, looks better. I hit continue. Oh, look, the shellcode printed. That must be the issue. Then I can go back and fix my shellcode, right? Of course, in GDB, you're not running as root anymore and so on. That's fine, but you can fix your shellcode and then rerun the program. All right, now that we've powered through, let's see what people are chatting about on Twitch. Okay, so the question is, why didn't I just GDB the shellcode as in the hello binary here and just, you know, start I and so on? I can do that as well, right? I can definitely do that. That's a perfectly valid thing to do. Someone pointed out on Twitch, or Hanto pointed out on Twitch, sometimes your binary, your shellcode runs in the context of the main binary and uses that context. It always runs in the context of the binary that you injected into, but sometimes actually uses that context. For example, sometimes you use file descriptors that the binary had opened, and so it would be nice to have your shellcode also have that that same context. Typically, the best practice is to debug things in as realistic an environment as possible. And so this helps a lot with keeping the environment realistic. All right. Let's see. Someone said something. Okay. And then some confusion, but we'll sort it out over office hours or recitation. Any other questions? All right. We have a request for calculating offsets for a challenge like string length hard. How can we make a proxy challenge for that on the fly? Let me show you string length easy. So offset calculation in general. Let me think if you want to. You showed offset calculation? Yeah, I would say my hint for this, for offset calculation, what string length does for offset calculation is add additional constraints onto your buffer, right? Where your buffer, when strlen is run on it, and all strlen does is looks for the first null byte, which read doesn't stop at for input, right? So you can happily send in as many null bytes as you want for input. strlen adds that additional constraint onto your buffer for the string length challenge. So string length easy and string length hard should be equivalent for offset calculation. My advice on all of this offset calculation stuff, if you're confused, calculate the offset for the easy challenge as if you didn't have source code or the debug output. And then you can guess and check your work. You can calculate and check your work.
And people should do that for any hard challenges.
Yeah, and in general, this is the point of the easy challenges. It's not just to give you easier flags. It's so that you can try to ignore the challenge debug output and still solve it in the normal way, right? But then you have ground truth that you can compare against. All right. I guess there was general. Okay. In terms of string length, people don't know how malloc and memcopy work. What's the problem with? Let's take a look at string lengths to see if we can offer some wisdom here. All right, let's take a look at what this is. Okay, so a couple of things on this challenge, right? That I guess we will give out as hints. So first things first, like the other challenges, this challenge will allow you to send 4 kilobytes of an entire memory page of input. But unlike these ones, the other ones, it will do a pretty common thing. It'll allocate a buffer perfectly sized for your input. It will be careful about checking the length of your input, right? And again, stir length. Well, we'll go into what these individual things do. And then it'll copy your input from that safe temporary buffer onto the stack. Now, where's the disconnect? The disconnect is that it'll copy as many bytes as you send, as long as the string length is shorter than some safe amount. So this 118 is, if we scroll up, is the size of your input. And that is what it makes sure that strlen, the string length of your input, doesn't go above. But it doesn't check that it received less than 118. You can send up to 4,096 bytes as long as strlen returns a small amount. All right, a couple of functions that you might not have seen, but that you should have seen before in your ASU experience writing C. malloc allocates memory on the heap of a given size that your program can use. So all this does is give you a buffer safely away from the stack. There's other issues with heap memory safety, which we would, for example, go into in CSE365, but it plops a buffer somewhere safe in this scenario for you to just use as your initial input, and it's correctly sized and all of that stuff. strlen calculates the length of the C string at that temporary input buffer. And what that does is it just sees how many bytes until the first null byte. In C, strings terminate on a null byte. And issues with null bytes are a very common problem in memory corruption in C binaries, with string length specifically. And then it mem copies your input. Mem copy will copy this much data, so the exact amount of bytes you received, from this buffer, your temporary save buffer, to this buffer. The stack buffer that we just confirmed was only 118 bytes long. So as long as you can pass this string length check, you can trigger this vulnerability. Now, just pass this string length check. Otherwise, all of your offset calculations and all of that are exactly the same as they were before. You just have to pass that string length check. Sweet. All right. Other questions on binary exploitation? Yes. Okay. Perfect question. So the question was, we now wrote this shellcode. Hijacked to map shellcode is I'm trying to think if you have time to go through it step by step. So if you wrote shellcode, say we figure out other ways to do it. You're talking about hijack to shellcode hard? To shellcode, yeah. So just take a look at this challenge real quick. Oh, fudge. God damn it. All right. This now requires you to send your payload including your shellcode and overriding the buffer. This is your only injection into the program. And if I remember correctly, yeah, you know where your shellcode is because we disabled ASLR, right? So if we run this guy, okay, practice mode is a good way to do this. We run this challenge. Okay, I'm going to show you one other really cool thing that it lives in /proc. And now we have to be root since we're running this legitimately. Actually, let's not run this as root. We're going to just run this challenge binary. Okay. As root, we're going to look at where it's PID. It's 608. Why does this say it's running as hacker? Okay, we're going to dig into that later. Okay, so it's in proc 608. Here we are. We cat out maps. These are the memory addresses of everything in the process's memory space for process ID 608, right? Here's where the binary is loaded, et cetera, et cetera, et cetera. And here's the stack at 4 FFFFFDD00. That's where the stack starts. Now, normally, with modern programs, you have a process memory layout that is randomized. So on a typical, like if I run cat, right? There's a pgrep cat. There we go. If I cat out cat's address space mappings, its stack pointer is loaded at something random. If I, let's just grep for stack. Here it is. I run cat again. It's completely different. It started out as 7FF D0F0. Here it is 7FF DAA0, right? Address space layout randomization means that every time the program runs, its address space is randomized. That means that you can't count on the stack being at the same place, which is the whole point, so that when you overwrite a return address, you don't know where to return to as an attacker. In these challenges, the way to bypass this is you need a memory, like an address disclosure in some way. And we have in the 466 material, we have a lot of challenges that explore this concept in different ways. In 365, in this very initial introduction to memory corruption, we just disable ASLR. So if we do this, and we pre-grab for this guy, and we do the same thing, oh, God damn it, it's the full path. Seriously can't pre-grab for this guy? Will this work? Will this work? Fine. Okay. So if I cat proc 1315 maps and grab that for stack, no, 1237, sorry. Okay, it's here. The first time I run it, and if I do that again with 1449, it's at the same place the second time. It's always at the same place for this challenge, right? Because we explicitly disable ASLR, and we do that with this crazy bit of code that you can see the effects of right here, where we run ASLR, no randomize, and then re-execute ourselves, which is a crazy thing to do, but it disables ASLR for this challenge. You can see it in the easy version. You can see how it does that, what the code looks like in C, but the TLDR is when we run this guy. Let's just make a big cyclic pattern just to, do we already have a cyclic pattern here? On cyclic, 20, dash L 2048. Or let's do the whole. Oh, that is the lookup, sorry. Okay, here's our cyclic pattern. It's 4 kilobytes. If we run it with a cyclic pattern, we have a crash. The crash is at the return at the return. So we overrode the return address and we're crashing, and we can see what this is, some part of our cyclic pattern. And where is our stack right now? Our stack is at this location. Where is our, if we actually just start it up, where's it reading our shellcode into? We can break here. This is the read call. If we look at RIP-2, it was at the syscall that it was sitting and waiting on input. And if we see where RSI is, that's the stack. That is where our input buffer starts, right? If we rerun this again, which normally would randomize, but since we disabled ASLR, will not, it's the same address. Is that correct? Yep, it is correct. So without ASLR, you can recover all of these addresses in the same way that you look at non-PIE address. They're all fixed addresses, execution after execution. And that's the way things were until really the late aughts, right? I remember participating in a hacking competition in the early 2010s, and they had address space layout randomization on. And I messaged the organizers and said, hey, you have address space layout randomization on. They're like, oh shit. And they turned it off because it was considered a very, very, very effective mitigation. But it's very new. All right, very new. It's, 20 years ago, everything was in fixed locations in memory. No one even dreamed about randomizing memory addresses. Well, people dreamed about it, but now it's a reality. But we're kind of in a learning about things from the historical context of where we can easily operate. One sec, we'll come back to you. There's an interesting question here. Can shellcode disable ASLR and re-execute itself? Yes, you could, but there's a chicken and egg problem. In order for your shellcode to start executing, you need to know where it is to redirect execution to it. Once your shellcode is executing, you don't really need to. There are other ways that it can figure out where it is. For example, using RIP relative addressing or a number of other ways to access the instruction pointer. So it's kind of too late, right? You need to know, you need either ASLR off or to know where the shellcode is before the shellcode runs. Yeah. All right, so here's a question. We run this thing in GDB. We look at the stack pointer like I just did. We get one value. We run it outside of GDB. Nothing fucking works. Why? Because GDB does a couple of things to the stack that end up shifting a little bit. And it's really frustrating. And specifically, the things that GDB does is add a couple of environment variables. Environment variables live on the stack, and so the addition of environment variables shifts the stack a little bit. This is really annoying. How to fix this? Well, you run the challenge, and then you attach to it in GDB.
With practice mode.
In practice mode. So we can start GDB, and instead of saying run, we say attach 2800. And here we are. We've now attached to GDB, and we can look at its stack address, or sorry, if you're interested in our SI here. Here's our SI, and it is BED0. I think in this case, it actually matched up. Nope, it was BEC0 when we launched the process in GDB, because GDB added some freaking environment variables. And it is BED0 when we run it ourselves. So it's hex 16 off. It's most likely going to be some multiple of 16, or not hex 16, hex 10 off. It's most likely going to be some multiple of 16 bytes. That's the error here. But that's the key thing, is that you can get the exact situation in practice mode by running the thing and then checking it in GDB. And then in non-practice mode, you might have to guess at the error between GDB and not GDB. Subtract 16, add 16. This is unfortunately not rare occurrence.
But once you've solved it in practice mode, it'll work.
No?
No, of course.
No, the host name's different. That's in the environment.
Sure.
Yeah. Yeah, the same offsets will occur between practice mode and real mode.
Wipe out your environment.
You could. So one thing that you can do is figure out exactly what the environment is or what goes wrong, and you can do env -I for wiping your environment and run it. And this runs this program with completely blank environment variables, which helps assuage this issue. And then it should be the same between practice mode and
Then you need
non-practice.
your exploits to run under the same conditions.
Yeah. You need to adapt your exploit, but then it'll work. All right. I think we just ran out of time. The next class is invading. Let's see. I think we covered the one thing we haven't covered that we should maybe do a stream about. Maybe we'll cover it briefly on Monday, or is the whole concept of putting the shellcode on the stack and redirecting to it. It's covered in the lectures, but we'll try to cover it in practice as well. All right. Awesome stuff. We will see you all next week. Have a happy, great Thanksgiving, and please don't delay on the chows. Good luck. Goodbye, hackers.